The focus directrix approach to parabolas is a slightly more sophisticated way of viewing a parabola, and it's based on certain applications and physical properties. So we're going to first take a look at the mathematical definition, and it's defined as being the set of points equidistant from a single point, which we call the focus, and a line called the directrix. So if we draw ourselves a single point and then a line here, we can then imagine what points would be equally distant from the point and the line. And so I'm going to draw this blue point, which is essentially halfway between. And we can move to the side, so it doesn't necessarily have to be along that perpendicular plumb line from the point to the line, but over here I can draw a point, and if I take the shortest distance to the line and the shortest distance to the focus, that point also would satisfy this condition. And similarly, as we go further out, this distance to the line and this distance to the point are approximately equal. And so you can see that as we draw the curve that goes between those points, and presumably that we would get something symmetrical on the bottom, this is the set of all of those points that would be equidistant from the point in the line. And so we talk about this focal distance P, which is the distance from the vertex. So the vertex occurs here at that nearest point, and then going to the focus. So here is the distance from vertex to focus. And this value P is very important regarding some physical properties. So there are lots of cool applications. One of those applications is just the simple flashlight. So if you kind of imagine a flashlight usually has this curved back where there's a reflective surface, and on the inside, typically you will have the light bulb not sitting right at the bottom, but it is set up just a little bit from the center and the back of that reflective surface. And the purpose of that is that as light is emitted from that source in all directions, the desire is for those rays to be pointed forward and all headed in the same direction. And so there is a focusing of that beam rather than just having it radiate in all directions. It again goes in a single direction, and that focus is caused by the position of the focus where the light bulb actually sits. So next time you go camping, take that flashlight out and take a look. Another interesting application is satellite dishes, very similar principle. But you have your satellite dish, and you have a collector, which sits here, and then on the back of the collector, you've got the wire that goes into your house. But as the transmitted signal comes towards that collector, it will hit the back of the satellite dish, and it will then proceed to go towards that collector, and then all of the various images that are transmitted will again be gathered here and then head its way along the wire towards your house. And if for some reason that little post gets displaced, maybe a bird comes and pecks it out of place, the transmission then will be lost. So for our parabola, we have these two equations which involve this important quantity P, the focal distance, and that focal distance is not familiar from the traditional representation of parabolas, but perhaps we can kind of explore how this looks in the parabolas that you've seen before. So I'm going to take the first equation here, and I'm going to divide both sides by 4p. So we get x minus h whole thing squared divided by 4p is equal to y minus k. And if I just switch the sides, I have y minus k is equal to, and I'm going to write that coefficient as 1 over 4p in the front, and then parentheses times x minus h whole thing squared. And this is very similar to the vertex form of a parabola, where typically the coefficient in front of the squared term, we called it a. So the 4p, again, can be translated to this coefficient that is more familiar. And we can see that there are both horizontal and vertical parabolas. So when you have the y to the first power and the x term to the second, it's going to be a vertical parabola, either face up or face down. And when you have the y in the parentheses squared and the x to the first power, then you're going to have horizontal parabolas. And the sign of p is important here because in this case, p will have the same sign as a, but when p is positive, it's going to be face up. And when p is negative, it's going to be face down. And that's for a vertical parabola. But for the horizontal parabola, when p is positive, it's going to be facing forward. And when p is negative, it's going to be facing to the left. So let's take a look at this example. And one thing about graphing using the focus Directrix method is that often you can't just take that formula, plug it, and plop it on the graph and have it all once and done. There's an interplay, there's some evaluation or assessment of the various features as you begin to graph them. And if you are able to work from equation to graph, back to equation, back to graph, you will find it to be easier and more successful, and you will require a lot less memorization. So the first thing that I do when I look at this is I notice that the y has both a second degree and a first degree term, but the x has only a first degree term. So that tells me then that the y is the quadratic portion, and then the y is what is going to have its square completed. So we will do a complete the square on the left. I've got y squared plus 8y, and then I need to add a needed number in order to make this a perfect square. And I'll take this number 8, divide by 2, that's equal to 4, and then I will square that, and that gives me 16. So on the left-hand side, the binomial that's going to get squared to produce that trinomial is going to be y plus 4 quantity squared, because again, the middle number, the 8, is divided by 2. Now on the right-hand side, I will rewrite what I've got. I've got 4x minus 8, but I added 16 onto the left, so I also have to add 16 to the right. And when I simplify this, then I'm seeing that I have 4x plus 8. So I'll pull the two sides together, and on the right-hand side, I'll factor out the 4 and get the expression 4 times parentheses x plus 2. Next, I'm going to pull back my two standard formulas for the parabola, which include the focal distance p. And I want to compare my example to the formulas, and I'm seeing that the y is squared, but the x is not. So I will then assume that this is going to be the horizontal parabola. And because I have the pieces in place, I can see that my center is going to be at hk, so the x, because there's a plus there, I will assume I'm subtracting a -2. And then the y value, I'm assuming that I'm subtracting a -4. Next, I want to look at this value, which is the coefficient, and that coefficient is equal to 4p. So I'm going to create a new equation. 4 from this equation is equal to 4p. And therefore, p is equal to a positive 1. And that tells me some important information. Because p is positive, I know that it's going to be facing to the right, as this is a horizontal parabola. So let's draw that. And we will assume that, again, our focal distance, which is the distance from the vertex to the focus, is 1 unit. So my vertex is located at the point -2, -4. And so I'm going to draw my grid around it, but I know that this is going to be in the third quadrant because both x and y are negative. And so I end up with something like this. Again, my value is going to be -2, -4 for that vertex. And now when I want to compute the focus, I'm going to see that it's going to the right. So my x-coordinate will increase by 1, and therefore the focus will have the coordinates -1, but the y-coordinate doesn't change, and so that coordinate will be -4. So let's go back to the original prompt. It asks us to find the vertex, and so the vertex coordinates we said were -2, -4. And next, it asks us to find the focus. And so the coordinates of the focus are -1, -4. And finally, it said to find the graph. Now, technically, we drew this sketch, which could potentially qualify as the graph. But if we wanted to draw a slightly tidier graph, we could start from scratch. But realizing that our vertex is a point on the graph, so I will put that point there, -2, -4. And we know that it is right-facing. And if we wanted to calculate another point, we could perhaps let y equal 0. And at that point, then we would have that 4x minus 8 is equal to 0, and therefore x would be equal to 2. So we've got the point 2, 0, and graphing this, then we have a point over here. So we can see that our parabola is somewhat wide, but it's drawn to look like that. So just to recap the process, I wanted to look at what we've done. The very first thing was we completed the square, and in completing the square, it told us two things. One is the position of the vertex, which we got by subtracting these coordinates. But secondly, it gave us the direction, vertical or horizontal, because we were then able to see whether it was the y that had the square or the x that had the square. Once we use that equation to find those landmarks, we then made a decision of which of these two equations, and in this case we chose the horizontal one, that we were going to equate the parts. When we selected our template, then we were able to find the vertex, which we actually could do without knowing that this was going to be horizontal. But what was really essential was then to pull off that p, that focal distance. And the focal distance then allowed us to show where that focus was in relation to the graph. And finally, when we went back to perform a tidier or nicer looking graph, we were able to put that vertex. So here's our vertex, here's our focus, and that distance as a +1, as demonstrating how we should draw our parabola.